So in my project where I'm trying to animate ChatGPT, I've been working on this project for a long time. And so this is what ChatGPT looks like once you download it from Hugging Face. And this, of course, is a still initial frame. So the goal of what I want to do is train ChatGPT and then show updated frames, because each time it trains, this image is going to change to some degree. And so training then is an animation. The animation will be of training. And so right now in my project, I've implemented both of the RAFK videos, and right now I have this test called SGD test, or stochastic gradient descent test. And you run this program, and it'll load ChatGPT2. It'll load this Shakespeare test data called Coronius, and the first 1024 tokens of the Shakespeare text, which ends here with bear. And then it will feed forward and make a prediction. And the prediction is 4, whereas the actual Shakespeare is us. And the cross interval loss is 4.2, and these other numbers are timing numbers. So each generation where it trains, the cross interval loss should go down, and it does. However, the prediction is wrong. And so the idea is, if this trained long enough and the cross interval continued to go down, that eventually it would say us equals us. And that happens at 6:31. This prints with a cross interval of 2.48. This prints us equals us. And so the time it takes to do a generation on my computer I made specifically for this project is about 10 seconds. So during the forward pass, the unembed is about 700. The forward layers is about 2000. So this is about 3. And then the attention, forward attention, is 1.5. And that is a large portion of the layers. Anyways, these are the backward numbers. The whole forwards and backwards takes about 10 seconds right now, and I think it can go faster. So let's look at this code. So this loads the Shakespeare test data. This sets up the first 1024 tokens and the next 1024 tokens for tokens in actual token predictions. What should be is the next tokens. So it prints it to the screen, and that's all of the text, Shakespeare text. There's a print function. This is predicted word, expected word, and then there's a do loop. Predicted equals feed forward. The predicted equals expected, print and break otherwise. Cross interval loss, backward, and SGD, print and increase generation. And this runs for 631 generations. And supposedly, I think what this means is that it has memorized the prediction, whereas before it was not exactly memorized because it was incorrect. It was a prediction that was not the true Shakespeare. So this forward and backward are covered in the RAFK videos. But stochastic gradient descent is a very simple addition, and it boils down to there are weights and biases that need to be updated in the network. And so during the forward pass, there were all of the weights, the various weights and biases, and they need to be updated with the backward pass weights and biases. And so both of these are passed to SGD, and SGD is very simple. It's just the weight minus weight equals weight minus gradient times learn rate, and the learn rate is 0.002. So this is what I'm going to animate, and right now this would involve somehow either somehow draw a frame to the screen after it has trained once. And right now it takes 10 seconds to do this before it could draw a frame. So that would not be real time unless maybe I get on the graphics card and instead of the CPU, maybe it'll be fast enough. But in the meantime, I'm just going to save the frame data to file, and then in a separate program, it'll display each of the frame datas in sequence. So I'll have to run this program a bunch of times, or for a lot of generations, to get like 10 frames a second is a good animation. And so one of these would be 1 frame. So yeah, I'm going to be making the animation segment now. We could look at so when I'm drawing this is a very large image. I don't necessarily have to draw, but this is a composite of all the various weights and biases in this single image. And when I'm animating, there's an option to only animate specific elements or a smaller model. This model is a full 1024 sequence. I could instead animate, say, a 64 sequence. And so there are two, and that might actually be really fast. Yeah, who knows what this timeline is going to look like. Um, but animation is next because I have a way to generate frames. And whether I need to go to the GPU at some point, I plan to port this to CUDA. But when, if I don't know. So we're going to take a break from this, and we're going to look at a space image. So this is a binary of an area called Pillars of Creation. This was taken with my dad's telescope. Now that my computer is upgraded, I hope to be able to view this without problems. So this is Windows 11. I don't know if this would be faster on uh, another operating system. I suppose. Nope, computer's not good enough. So these are the same color modes that are going to be used to view the neural network. This is essentially how they work. Okay, I'm going to look at so this is what the network viewer, my old network viewer, looks like. This is the status of wherever it left off. So this is a bunch of weights in an MLP and stochastic gradient descent, a larger number. So when this animates, has a load time. So this is generating the animation in real time, unlike what I'm going to do at the moment with ChatGPT, which is not do it in real time. This particular network is a connector network. which is smaller networks that I connected together into larger network. And so look at this for a little bit. This is what I am going to be doing with ChatGPT, because the color format can be determined in real time, rather than having it all be in one color format. That's going to be determined at real time, just like it is now. So when I make it train, these next tokens and tokens are going to scroll across the Shakespeare. Rather, right now, every time it trains on the same sequence of Shakespeare. And so by the end of the process, 600 or so generations, it outputs the correct thing. I think it can go faster. Here's it running on the CPU still. So the first generation is slower generally. So this computer looks like this when it's running. So what can happen is that this training process can be expanded to have more batches, or future the remaining GPT-2 model sizes. I assume these shapes would get larger. That's it.